pitch black, crushingly cold, under pressures that would flatten a submarine. Somehow, entire ecosystems flourish here in a world of complete darkness. Forget photosynthesis. Down at depths past 1,000 meters, life harvests energy from chemicals bubbling up from the planet's crust. How does anything survive in this abyss? The answer rewrites what we think is possible, and it all begins with a discovery that changed science forever. Descending through the ocean's layers, sunlight fades quickly. By 200 meters, about the height of a downtown skyscraper, light has vanished. The twilight zone stretches from 200 to 1,000 meters, a place of dim blue shadows. Past that, in the bathypelagic and abyssal depths, darkness is absolute. Here, the pressure climbs relentlessly. Every 10 meters adds another atmosphere, so at 3,000 meters, the weight is 300 times greater than at sea level. In the trenches, like the Mariana, plunging nearly 11,000 meters, pressures soar above 1,100 atmospheres, enough to crush steel. Temperatures in these depths hover between 2 and 4 degrees Celsius, just above freezing, and they never rise. No sunlight ever reaches these zones, making photosynthesis impossible. Life must find other ways to persist. The animals here are shaped by these extremes. Many have soft, gelatinous bodies without air-filled spaces that could collapse. Jellyfish and siphonophores drift with the currents, their forms adapted to survive crushing weight. Fish in these depths often rely on oil or fat for buoyancy, since gas bladders would implode. The deep sea is not just a place without light. It is a world defined by pressure, cold, and a constant struggle to endure. Every survival strategy begins with these unyielding barriers. In 1977, a deep-sea submersible called Alvin descended to the Galapagos Rift, 2,500 meters below the surface. Instead of barren rock, scientists found dense clusters of giant tube worms, clams, and crabs thriving in the darkness. These hydrothermal vents, where seawater meets hot magma and erupts back into the ocean, release scalding fluids rich in hydrogen sulfide and methane, chemicals toxic to most surface life. Here, bacteria use these chemicals as fuel, oxidizing hydrogen sulfide and methane to create organic matter. This process, known as chemosynthesis, forms the foundation of an entire food web that owes nothing to sunlight. Giant tube worms, Riftia pachyptila, are icons of this world. They have no mouth or gut. Instead, they house chemosynthetic bacteria inside a specialized organ called a trophosome. The worms absorb sulfide and oxygen from the vent water, and their hemoglobin binds both, delivering them safely to the bacteria. In return, the bacteria transform these raw chemicals into sugars and nutrients that feed the worm. Vent crabs, Bythogrea thermidron, graze on bacterial mats or prey on other vent dwellers, all ultimately reliant on these microbial producers. Dr. Cindy Van Dover, a pioneer in vent biology, describes it this way. At vents, bacteria oxidize hydrogen sulfide and methane to produce the base of an entire ecosystem. Tube worm fields and vent crabs thrive without sunlight. The discovery of chemosynthesis at hydrothermal vents revealed that even in the deepest darkness, Earth's own energy can sustain vibrant communities. Life here is powered not by the sun, but by the planet itself. In the deep ocean, where sunlight cannot reach, animals create their own light. This phenomenon, called bioluminescence, is powered by a chemical reaction. Luciferin combines with oxygen, and the enzyme luciferase triggers the reaction, releasing a glow that wastes almost no energy as heat. Most deep-sea light shines blue-green, between 470 and 520 nanometers, because these wavelengths travel farthest through seawater. About 3 out of 4 deep-sea creatures, from jellyfish to fish, use bioluminescence. The anglerfish, for example, dangles a glowing lure filled with symbiotic bacteria to attract prey in total darkness. The Atala jellyfish flashes a brilliant spiral of light when threatened, a display that can summon larger predators to scare off attackers. Oceanographer Dr. Edith Witter describes bioluminescence as a language of survival. She says bioluminescence is produced chemically inside the animal, used for lures, mating flashes, and counter-illumination. In this world, light is currency, weapon, and shield all at once. Survival. In the deep sea demands more than just tolerance for darkness. The barrel-eye fish, for instance, has a transparent head and upward-facing tubular eyes, allowing it to spot the faintest glimmers from bioluminescent prey above. These large, sensitive eyes maximize every photon in a world where light is a rare resource. Other species, like the tripod fish, rely less on vision and more on mechanoreception, sensing tiny vibrations through elongated fins that rest delicately on the seafloor. Instead of gas-filled bladders that would collapse under pressure, many deep-sea fish float using oils and fats, substances that resist compression. Their bodies are soft, flexible, and their metabolism runs slow, conserving energy in a place where meals are few and far between. Every anatomical detail, from the shape of an eye to the chemistry of a cell membrane, is tuned for survival in this crushing, silent world. Food drifts down from above as a slow, constant rain of organic matter, marine snow, tiny flakes of dead plankton, fecal pellets, and fragments of plants settle through the water, nourishing life far below. But in the deep, this trickle rarely satisfies. Most animals must wait for something bigger, a sudden windfall like a whale fall. In 2019, the ROV Hercules recorded a whale carcass at 3,200 meters. Hagfish arrived on the first day, burrowing into the flesh. By the second week, crabs and amphipods crowded the bones. Months later, chemosynthetic microbes took over, breaking down what remained. Dr. Craig McLean describes it simply. Food is rare. Deep animals live slowly, and they wait for whale falls. Every scrap counts. Scavengers, ambush predators, and microbes turn scarcity into survival, making the most of each fleeting feast. Life thrives where sunlight never reaches, reminding us that nature always finds a way. As deep-sea discoveries accelerate, the boundaries of what is possible grow deeper still. What limits remain unchallenged?